Hello, everyone, and welcome to this new webinar of physics. And it's a pleasure this time to have here to Aurelio Carnero-Rosell. He will present some results about the DAS, the Dark Energy Survey telescope, and well, in relation with the cosmology. And well, the last week was very active for these webinars of physics, because we have a celebration of the 50 webinar, and also we have this Dark Matter Day that I invite you to follow on the YouTube channel that we have. Well, just visit this and give us some likes, okay? And well, I would like to remind you that, well, you can ask questions to Aurelio in YouTube, in the chat of the YouTube, I think around here. And well, some words about Aurelio. Aurelio did his PhD in CMAT in Madrid, and he is now a postdoc in Rio de Janeiro in the National Observatory in Brazil. And in the Laboratorio Interinstitucional de Astronomía in Rio. Okay, and well, Aurelio, thank you very much for being here. And well, if you want to say something starting, or if you want to start sharing your slides, please go ahead.
Thank you very much. Can you hear me?
Yeah, we hear you perfectly.
So I hope you are seeing the slide. Thank you all, and thank you for the invitation. I would like to speak today about the most recent results from the Dark Energy Survey. Compromises the first year of observations. My name is Aurelio Carnero, and I'm working at Observatorio Nacional in Rio de Janeiro, inside the Laboratorio Interinstitucional de Astronomía. So basically today, first I will do a brief introduction about dark energy, how we can measure it from the sky, and what are the current constraints on dark energy. Then I will do a basic introduction to gravitational lensing, which has been the main method to obtain these first year cosmological results in the Dark Energy Survey. So after the introduction, I will talk about the status of the survey, and finally talk about what it's important today, which are the new cosmological results. I would like to thank to Daniel Gruel and Judy Pratt that some of the slides, I took it from past lectures from them, but we are colleagues, so that's not a problem. To start with, think about the universe. On larger scales, or the universe is described as an homogeneous fluid in an expanding universe. In common sense, when we look around, we see that gravity exists, and gravity likes to pull things down, to group things. So in principle, when we think about the universe, we would assume that the universe is made of matter, and this equation is the field equation of general relativity, where the dynamic of the universe is contained in the Hubble factor, which is this A0 divided by A, where A is the scale factor. Basically is how much the universe expands in a time interval, and the expansion rate, which is the acceleration of the expansion, is given by A0. So this would be like the common first approach to the universe. We have matter and other species like radiation and neutrinos. But then in the end of the 20th century, we discovered that actually there was another contribution that is making the universe to expand in an accelerated way. In a universe with only matter, we would expect the acceleration to decrease. But observations actually tell us that the expansion rate at this time is actually accelerating. It's positive acceleration. So in the field equation, we have also a solution adding a constant. So this constant could be associated with this effect that is making the expansion to accelerate. That's why the dark energy is normally associated with the cosmological constant, which would be the easiest model which could integrate this effect into the equations. So we have these terms that are unknown in principle, which is the density of matter and density of energy, of dark energy. In order to close the model, the actual model, we need to add 4 additional free parameters. One is sigma 8, which is the amplitude of density fluctuations, the ratio of neutrino masses, the rate of expansion today, and the scale dependence of density fluctuations. In the current model, based on observation, we are actually measuring that the universe and energy density is made 70% of this unknown term that we can associate with the energy of the vacuum. Also 25% of dark matter and 5% of ordinary matter, which is baryonic matter. So just to give you a hint of what this model can explain, we have observation of the very early universe, and we can make a photo of the cosmic microwave background, which is a remnant radiation coming from the Big Bang, or when the universe was very hot and dense. And the temperature distribution, it fits exactly with that of a black body. So the universe was very homogeneous in the early universe. But then when we go to late time, which is in our current time, we actually see that the distribution of matter is very clustered, is very condensed in clumps and filaments, which are these structures here that we can see on data, on the plot from Sloan Digital Sky Survey, and on the back of the images is a result from simulations. So this model, assuming that the universe is a perfect fluid, it's actually able to explain how structures grow from a very homogeneous universe, because here we see inhomogeneities, but these are on a scale of 10 to the minus 5 in density. So the universe was very homogeneous, but today it's very clustered, and we can explain this with this model. So, as I said, this is a quite odd model in the sense that most of the content of the universe, we don't know what it is. 70% of the energy is an unknown substance that appears like vacuum energy, although there is a drawback that the standard theory of quantum field theory predicts 120 times a bigger energy density than what we observe in the universe. Also, 80% of the matter is unknown in the form of dark matter that only interacts via gravitation. But fortunately, even if it's so, that actually we have a lot of independent observation that sustain this model. This model is mostly phenomenologically together with the equation of general relativity. But the free parameters that I said, amplitude of fluctuations, the content of energy, matter, neutrinos, these are all free parameters that we need to constrain. So some of the questions that we can ask to start investigating about dark energy, that we might find hints about the nature of or the content of dark energy in the universe, is if we are the physics of the early universe, which is, for example, this image from CMB, and the physics from late universe, which is this image where we have galaxies and cluster of galaxies, are those fitted by the same parameters? also, do measurements of cosmic distances and growth of a structure agree? Also, we can try to look at changes in the energy density of dark energy. Basically, what this means is trying to obtain the equation of a state of dark energy defined as the pressure divided by density. If we can find variation through time of the equation of a state of dark energy, this will imply that dark energy is not the cosmological constant, for example. So these are some of the observables that nowadays surveys try to answer, looking at the late universe and comparing with early universe, measurements of cosmic distances and growth of a structure in order to obtain the equation of a state of dark energy. So how do we observe dark energy in the universe? We have basically dark energy enters into observation in two different effects. One is it actually modifies the rate of expansion. As many dark energy we have in the universe will expand quicker. Another, the dark energy is sensitive to the growth of a structure, which means, as we said, in the early universe, the universe was very homogeneous, but today is very structured. We have filaments, galaxy clusters. So that is the growth of a structure through time is sensitive to the amount of dark energy in the universe. So the question that we need to ask is, do all these measurements agree with predictions in the same fiducial lambda cold dark matter model? And the answer is, for now, it looks like. So now I'm going to explain the current status of observations of dark energy. Basically, the expansion history observables, that would be, which in this previous slide, I'm talking about CMB, BO, and supernova. The idea is that we compare known distances or known objects at different times, and we can create like a distance ladder from the early universe to today. And that's what different surveys have done here, measuring the BO scale. So one method to study the expansion history is to look at standard rulers. Imagine that we know a physical distance that is imprinted in the CMB, and then this physical distance can be later measured in late-time universe, looking at the galaxy distribution, and then we can compare the size of the scale. This is what I'm showing in the top plot. Basically, the gray area is the measurement of the sound horizon in the early universe, when the universe was 1,800 years. And today, in the galaxy distribution, we can measure the same scale, but expanded at later times. And in the distribution of galaxies, this is called baryonic acoustic oscillation, or BO. So as we can see here in the top panel, the agreement between the measurement of the sound horizon is in gray, and how the prediction of this sound horizon scale at different redshift, they agree. It agrees with the measurements done at late time using 6DF, SDSS, BOSS, and Wiggle-Z. Another case to study the expansion history is to look at standard candles. Imagine that we know the intrinsic luminosity of an object, of an event in the universe. If we observe at later times or at different times, we will see a dimming of the light, and we can correlate to obtain the distance. This has been used. Fortunately, we have supernova type 1A that are considered as standard candles, and we can plot its magnitude as a function of redshift, and we see that the prediction of the CMB, which is the gray line behind the points, agree very well with our with the current measurements of supernova. And these two measurements give very tight constraints on dark matter and dark energy. Another observable that we have to measure only the growth of a structure is the redshift space distortion. Basically, I won't enter into details about here, but basically the redshift space distortion effect, what it measures is in a cluster of galaxies, we measure redshift to obtain their distances, but these galaxies have peculiar movements where the galaxies infall into the cluster. So we can measure blue shifts and red shifts on top of the expansion redshift, and this can be measured to give us a hint of the strength of gravity at that time. And the measurements today, they are all agree with a fiducial lambda cold dark matter, which is signalized in this plot with a gray band, which are the results coming from CMB experiment. So these plots are showing that late time measurements with these galaxy surveys agree with measurements of the early universe. Then we have the other observables like the galaxy cluster number counts. This observable depends both on growth of a structure and expansion history, and basically we measure the amount of galaxy cluster as a function of redshift and mass, and it is sensitive to dark energy in a sense that is actually very good to separate, to break degeneracies of other methods. For example, this plot on the right is based on simulations. We see that the clusters add quite good constraints to other observables like supernova in green, CMB, which is early universe, and BO, that is late time universe. So it's promising, it's very promising the use of galaxy clusters to improve the constraints on dark energy, although the results that I'm presenting today, we are not using cluster number counts yet. Again, all these results are consistent with fiducial lambda cold dark matter. And now I'm going to give a brief summary on gravitational lensing, since it's the main method used in DAS. Basically, when light passes through massive structures, it feels gravity and its path will get bent. That is why this effect is called gravitational lensing, because it's similar to an optical lens. So this distortion causes shifting and magnification of the images of background galaxies, as well as a shear. So here on the bottom, I'm showing some example of some extreme gravitational lensings, where in the center we have a bright galaxy, yellow, and then there are these rings around, which are actually images of normal galaxies, but the images has been sheared due to the mass of the galaxy in front. So the method that we use in DS is basically measuring the shear of galaxies around galaxy clusters in order to obtain a mass map. Because this method is only sensitive to the amount of mass which is in front of the galaxy. So the shear of the galaxy is a function of the mass that finds in its path to us. So this is more like a visual image of what the shear image is. Here, maybe it's not very clear, but for trained eyes, you can see these yellow points that are bright galaxies, and on the back there are a lot of blue small galaxies. If we would measure the shears of the galaxy, we will see that they are correlated with the position of this galaxy cluster, telling us that they're giving us an amount of the matter that is in front of us. Remember that most of the matter is dark matter, is not luminous matter. So we could not make the same, we could not obtain the amount of shear if we only count the visible mass. We really need dark matter to match to our observations. So recent results from cosmic shear from gravitational lensing claim to have detected a 2-3 sigma offset from measurements of early universe, which is CMB, versus late-time universe obtained from galaxy surveys with kits and C-fetch the lens. But the thing is, like, is this effect comparing the red circle, the red contours versus the green one? Is this a non-issue? Is this actually statistically significant? Is this maybe pointing to a crack in the model, or is maybe a systematic error from the surveys? So this was kind of the answer that we tried to, well, that's the question that we tried to answer with this first year analysis. If this effect, if we could see this this offset in the DS data and if it was significant. So going to the dark energy survey, now I'm going to explain the results from the first year's observation. The dark energy survey is an imaging galaxy survey mapping 5,000 square degrees of this in the southern hemisphere in 5 years. We are already in the taking the 5 years observation. Still, we are only presenting the first year observations. We are still having 4 years ahead of us to analyze. It's we are using a camera in the Blanco telescope in the Cerro Tololo Inter-American Observatory in Chile, observing in 5 filters covering the optical, GRI, and the near-infrared Z and Y. This is the footprint of the area that we have observed. The results that I'm presenting today are based on what is shown as red in this plot, covering around 1,500 square degrees and covering the observation from 2013 to 2014. So the results I'm presenting today, of course, are not only mine. This is a great collaboration of more than 400 scientists. And actually now they are meeting in Brisbane in Australia, where it's happening the DS collaboration meeting. And this is a photo from the previous one in Chicago. So we are universities from the US mainly, but also England, United Kingdom, Spain, Brazil, Australia, Switzerland, and Germany. So in DS, for the year 1 results, we didn't use only weak lensing, but we could cross-correlate with results of large-scale structure, which is basically the distribution of galaxies in the universe. So with these observables, we measure the positions of galaxies that has been lensed, that are tracing the large-scale structure. And also we measure shapes of these galaxies. Then we can combine the measurements of the galaxy autocorrelation function, which is basically proportional to the density of galaxies. Then we can measure directly the pure cosmic shear, which is a correlation of shapes and shapes. And this is proportional to the density of matter. I didn't explain, but the density of galaxies, here you can see this small formula, is given by a galaxy bias, B, times the density of matter. Bias give the ratio of galaxies as a function of the matter field. But also we can make a cross correlation between cosmic shear and galaxy autocorrelation function, and this will be proportional to the density of galaxies times the density of matter. So these are the 3 formulas of observations that we are going to measure from data. And finally, combining these measurements, we get the best constraints on year 1 data. So the measurement of the shear, it gets us directly to the content, to the mass content. Looking at the autocorrelation, we need to look at galaxies, which have this bias that sometimes can be unknown, but cosmic shear actually looks directly to dark matter because it's made of 80% of the matter is dark matter. So basically, we can make a map of the matter content due to the shapes, due to the shear of the images of the galaxies. And this is one of the results of the survey. We have created the biggest matter map up to date and covering from Redshift 0.2 to 1.3 by looking at the shear of galaxies. So with this map, we can study the dark energy content at late time of the universe. But to get here, this is important, I think, to remark that we are entering, the dark energy survey enters into the realm of big data. So we had many different, we had to carry a very detailed analysis of the data that we take from the telescope. We created the gold catalog that you can see in Driekau, Wagner et al. Paper. We create red magic galaxies. We calculate the shear catalogs, and we finally obtain the galaxy clustering and cosmic shear. But to do so, we also need to understand the redshift distribution of the galaxies. We did a very robust analysis of systematics to get to the final results. I'm putting this slide as well to reference many of the authors of this analysis that you can find today in the archive and also in the Dark Energy webpage. So, as I said, with big data demands a great we have great statistical power. We need a great systematic analysis. Since we have an unprecedented size and depth of photometric data, this has been very well calibrated. Then the shear measurements has been measured by completely two independent codes and calibration and both pipelines actually agree on the results. We did a full treatment of covariance matrices, including nuisance parameters, which are those that we might not know their value. For example, uncertainties in redshifts, uncertainties in neutrino mass. And then before we produce the results, we tested in simulations and in theory, and we applied two different MC codes, cosmolike and cosmosis, that gave us also the same results. So we developed a machinery to be sure that we were obtaining robust results from good data. What is a novel thing that we did, again, this is the mass map that we obtained. So measurement of cosmic shear, as I explained earlier, light passes through distant galaxies, and when it passes, their light path gets distorted, and we can measure the shapes, and also we measure correlation of shapes of galaxy pairs. We created a catalog of 35 million galaxies, and we measure with a different independent method, and we got the same answer independent of the algorithm. So the measurement of cosmic shear during the analysis, we were very aware of not being blind, of not being biased by our perception of the data. This is an important issue that is starting to be common, at least in galaxy surveys, is that we need to make the preliminary tests on blinded, which means, for example, if we look on the plot, we can see on the top, we can see the results from Planck in red, and in orange, the results from other galaxy surveys. And here we have our constraints, but there has been shifts, so we don't want to know the value yet. We only reveal the results when we have passed all the tests and all the systematic tests. So, of course, our result is not here. It has been shifted, so we are not biased by our perception. Imagine that we find a discrepancy, and maybe we say, this discrepancy I don't like, maybe I have done something wrong. So to avoid that, let's be sure that we have everything right, and then we look to the result. So, as I said, we will not use only Shear, but we use also galaxy clustering. The combination of these three joint analysis maximizes the use of information, and this is the largest individual data set and joint constraint from these three probes for the first time. So this is a novelty in the community. So combining these three observables, what are the consistency of the individual constraints from these three observables? No, we have matter density, the cross correlation, and the shear measurement. So these three observables give us similar results. We are not showing the results yet. This is only to see the consistency of the different measurements. And we use the criterion of the bias factor, and also we did other systematic tests to demonstrate that the three observables are consistent, and they give us a bias factor of 2.8 for the three hypotheses: the shear measurement, the cross correlation, and the autocorrelation of galaxies. And this is already one of the results. So as you can see, we agree to 1 to sigma with Planck, which are results from early universe, versus our results that are late time universe that are in orange. So as I said in the start, when I talk about gravitational lensing, there seemed to be some discrepancy between early universe and us. And I say, okay, was that significant or not? We are also finding an apparent minor discrepancy, but is this really a discrepancy? Well, actually not. If we look at the bias factor, the results from Planck agrees with those from DES in the sense that combining a central value that would be represented by the green line, if we measure it with two different experiments, can give us the results that we obtain. So basically, we haven't found any discrepancy with Planck. Therefore, we can combine the results from Planck and DS to get even tighter constraint on the sigma 8, and which is the amplitude of fluctuations and dark matter. So following the analysis, then we further add other late time physics, which is low redshift, means we are near our time. And so we join our analysis with other measurements from baryonic acoustic oscillation and supernovae, and we actually obtain tighter constraints on the late time measurements in orange than using only DS data, which is these contours here they got reduced, and they are still consistent, although it is true that the discrepancy is in the same direction that we have found in previous surveys. We cannot claim to be a discrepancy. So Planck and Galaxy surveys agrees on this. So finally, combining all late time experiments and CMB experiments, we get these very tight constraints on equation of a state of dark matter, the Hubble parameter, and other cosmological parameters. And we have obtained the most precise measurements of the lambda cold dark matter parameters with a density of matter of 0.3, and absolutely no evidence for varying equation of a state of dark energy. So this is telling us that the lambda cold dark matter is working very well, agrees very well with our observations. One note that I forgot to say, but I think it's important, this plot, this is the first time that a galaxy survey reaches the same resolution as CMB experiments. So this has been a major result is that we finally get the same resolution as CMB. for these cosmological parameters. So getting to an end, so what's for the future? What I've presented here is a very precise test of the lambda cold dark matter model, and it shows that we haven't found any discrepancies with previous measurements of the CMB. But of course, this doesn't explain what is lambda cold dark matter. It doesn't explain what is dark energy or dark matter. This is due because this is not very sensitive to models of time varying dark energy. But for the year 5, if we join the results from weak lensing with galaxy clusters, this will break the degeneracy. And here is a forecast on the plot. And in the middle, we see the resolution of GR5 when it's finished, when we finish the analysis. So pay attention for the future, since DS in principle will be able to give tight constraints on the possible evolution of the dark energy equation of a state. So finally, we've seen that there are a wide range of probes from early and late time universe with geometry tests that agree on a common fiducian lambda cold dark matter cosmology. DS with GR1 observation has added most of the precise measurements of a structure in the late time universe. And the results are competitive and consistent with Planck CMB results. And this claim offset between Planck and late time surveys is insignificant, and we can give precise joints measurements which gave us the results that are expected. In the sense, a density matter of 0.3, an amplitude of fluctuation of 0.8, and an equation of a state of dark matter equals to -1. So in the next years, we will combine with more data and with other observables to improve what we have done so far. So thank you. And please, we are open to questions.
Okay, thank you very much, Aurelio. It was a very nice talk. Well, now we have people here in the room that I don't know if any of you have questions or some comments about the presentation.
I have one. Can you guys hear me?
Go ahead, Nicolas, please.
Okay. In the just before the summary, Aurelio, you say like it was written that it doesn't explain lambda CDM. I am not sure to understand what you mean.
What? Let me, sorry. Yeah, my computer got trying to find the where?
I think it's the previous one. So slide 36, I think.
Yeah. So
yes, right. So you say it doesn't explain lambda CDM.
Exactly. So to explain lambda CDM, we need to answer which is the equation of a state of dark energy. So far, we can measure the density, basically the amount of dark energy with this weak lensing probe. We can measure the density of dark energy, but we don't know if the equation of a state of dark energy evolve or if it's equals to -1, which is for the energy of the vacuum. So this method is insensitive to the equation of a state of dark energy.
Okay, I see. Thanks.
I have a question regarding this comparison with Planck results, because what you have there is, if I see correctly, you have like less omega matter, right? There is some reason why DAS point to this lower value. I mean, Well, I
Yeah.
know that it's not exactly what you are measuring here, but it's just this correlation. But why?
It's a good question, because it is actually also related to this other problem that I don't know if you have heard about it, which is the measurement of the expansion rate, the Hubble constant. Measurements of CMB experiments give, I think, are lower values of the expansion rate, while high rate, like galaxy surveys, give higher rates of expansion. And this value is actually very correlated to dark matter also. So they are coupled. So this discrepancy might be related also to the discrepancy of the Hubble expansion rate.
Yeah.
But those effects are together. So I don't know if this shifts. If we fix the Hubble constant, if we imagine, okay, we know Hubble constant is 70, probably this discrepancy wouldn't be present. Yeah. So it is related to also to the Hubble expansion rate. Yes. But of course, I mean, it is not significant, so maybe we cannot say that there is a discrepancy, but it's also related to the Hubble expansion rate.
Oh, okay, thank you. Any other question here in the room?
Yes, I have a question. Can you hear me?
Yes. Yeah. Go ahead, Joel, please.
So I was wondering if the combined fit gives any further constraints to parameters like the sum of neutrino masses, for instance.
I think that there was someone in the collaboration that looked at, but actually I think we are, again, we are not very sensitive to neutrino masses yet. The biggest constraints come from CMB, from early time. But I think there's been a paper that put constraints on neutrino masses, but sorry, unfortunately, I don't know the details of the result. But I know someone looked at. But the increase on resolution is not great. Probably we have to wait till the 5-year results, when we combine with galaxy clusters and supernovae, that we might have an answer to the neutrino masses. But it's been looked at, of course, it's been looked at, but nothing significant yet. So constraints are almost the same as in the early universe.
Okay, thank you.
Thank you.
Any other question here?
Yes, I have another one.
Yeah.
Go ahead.
So at the very beginning of your presentation, Aurelio, just before talking about the DES experiment, so you were talking about the cosmic shear and this tension with the lambda CDM.
Yeah.
So just to be clear, this tension is when you compare high and low redshift, right?
Exactly.
Okay. Yeah, I was not sure.
Exactly. CMB means cosmic microwave backgrounds. That is when the universe was less than 400,000 years old.
Yeah, but it was confused because in this figure you cannot see really a tension, no? I mean, all the blob seems to.
Yeah, no, exactly. I mean, I think it was too early to say, and I think it was a claim by Kidd's team. I think Kidd said, okay, I think there is a tension, and that spread on the news and spread on the community. But basically what we are showing in our result is that that tension is not significant. It's just,
okay, I see.
It's a non-issue for now. But it's true that it's in the same direction, but it's a non-issue. And of course, when I see this figure, I always get surprised. Okay, Planck is more recent, but if you look at WMAP, there is the same result. So I kind of repeated this because it's kind of common today, a hot topic. But for me, it never was such an issue. But at least I wanted to create some controversy. Because if not, it looks like, I mean, the lambda cold dark matter fits very well to the data. So at least I want to give some uncertainties.
Okay, and the last question is, how long is DES supposed to take data?
So in principle, it should finish now in February. During 5 years, it has been using 5 months of the Blanco telescope, the best nights to the survey. So we are ending the 5 year, but it might be an extension for a 6th year, since we have In the middle, we have one very bad year because of the Niño, and we could only take almost half of our exposures. So it might be an extension for a 6. That means that probably by 2020, I guess that we would have final cosmological results, or maybe earlier, 2019 probably.
Okay, thanks.
Okay, thank you very much. Well, I don't see any other question or comments here. Then I think we can say thank you to Aurelio for this very nice talk. And well, it was well. We will have this. We hope to have these slides in our web page in the near future.
So yeah, I mean, when I close the room, I send you the slides.
Okay, perfect. That will be great. And also, well, this video will be on YouTube. You can watch this
and send to my family
as you like. And then, well, thank you very much also to all the fans.
I will follow these talks from now on because.
Okay, that's great. Because well.
I think, I mean, it's funny, but we never here in my observatory, no one knows about these talks, maybe about, I don't know why, the dissemination.
Yeah, well, anyway, we are trying to make more publicity, also inviting.
That would be great.
Okay. And well, in 2 weeks, we will have another webinar. And well, just follow us in our social networks. Okay, thank you very much, and goodbye, everyone.
Bye.